Hey team, let's have a talk about position vectors as a function of time. So, bit of a reminder from things we've done previously in vectors. So, when we're looking at something in Cartesian form, we have something in terms of x and y and z if we're in 3 dimensions. Parametric form, we can have separate functions, x as a function of t and y as a function of t in 2 dimensions. But we'll also have z as a function of t if we're in 3 dimensions. If we have the position vector, rather than having 3 separate equations, what we do is we put them all together in an equation like this. This will look vaguely familiar compared to the things we've done in the past. We had the x as a function of t, we put that with the I vector component. We had the y's with the j's and z's with k's. That makes sense. And remember, position vectors have their tails at the origin. They're a vector that start at the origin and point to a particular point. So you'll notice here, these dotted lines, these are all position vectors. And just like when we've been dealing with position vectors in the past, we have it pointing from the origin to a particular point. And that position vector will change. Here it is at t equals -1. Okay, we're going to negatives. Here it is at t equals 3. And the end point of that vector, the head of those vectors, are pointing to a particular, in this case, line. So imagine that the vector is like a pen, and the tip of the pen is drawing out a line. And the reason we start from that origin is I like to imagine it as maybe this is an air traffic control tower and it needs to be able to point at a plane over various points in time and need to know the position and distance and direction, all that kind of stuff. We've previously dealt with this with just lines, but we can have heckin' crazy things like this spiral as well. Now, these are all called the graph of a vector function. It's not function in the way that you've experienced function in the past. It's more talking about it maps real numbers to vectors in a multi-dimensional space. It's not talking about any vertical line test situation here. So a little bit different terminology-wise there. If you want to do some more basics with vector function work, have a look at the 13A questions. It talks about some basics like finding domain and range. Domain would have to do with the x parametric equation, range would have to do with the y. But when we're talking in 3 dimensions, we've also got that z, so, things get a little more exciting there. We can use this information, that vector function, to map the motion of a particle, and we can look at that instead of the Cartesian equation for its path because it actually gives more information. Not only does it give the position at various times, it also gives the direction of motion. Position at various times can also be done using the Cartesian equation. That also works. But the direction of motion, much better to have our vector function. The speed of the particle, we can use the calculus part of vector calculus, which we'll be talking about in a little bit. You're going to frequently need to use your trig identities for this work, so please make sure you're referring to your formula sheet. Now, I'm not going to go through this bit in detail. I can put some resources up about reviewing conic sections, but just a few reminders about the equations of circles, ellipses, hyperbole. How do you say the plural of hyperbola? I don't know. And we've got the Cartesian equations here. We know they're Cartesian because they're in terms of x's and y's. And we've also got here these vector functions, or I should say position vectors. Because remember, terminology-wise, the graph of a vector function is the set of points determined by the function r of t as t varies. So, some great stuff there. We've got it, as you've seen in the past when you looked at the parametric equations for your circles and ellipses, for example. This has got it in terms of that position vector r of t. And we've also got some hyperbole action as well, where we've also got some cosec's and cots and stuff going on as well. So have a little look-see at that. A little reminder about how you found asymptotes for hyperbole. This talks about when you've got something centered at the origin, but then it expands out to look at things not centered at the origin. So just a reminder of how to find those asymptotes. And the direction of motion, again, that's not encapsulated by those Cartesian equations. Being able to know which direction. So for example, if you substitute t equals 0 here into this, you're going to get this point. If you substitute in t is a half, you're going to have, well, first off, your vector would have pointed t equals 0 then your vector would have pointed here. Then when you substitute in t equals pi, you will have a vector pointing from the origin to there, and then from the origin to there. So that gives us a direction of motion, which is the endpoints of those, meaning this particle is going to be traveling like this in a circle. Not a circle, very much not a circle, in an ellipse. Also got some examples for some hyperbole here. And we've got, these ones are interesting. They start here and then travel off. And then they go like this. And then they come back to finish it. So have a little look at the directions that these are going as well. So we can sketch those on a Cartesian plane if we're dealing in 2 dimensions, of course. What you could do is, you'll notice we've got something here and a position vector r of t. You could substitute in values of t and then find the corresponding values of x and y. Or you could convert the parametric equations into Cartesian equation and sketch that. It's really important to note though, the direction of motion needs to be noted. So we're going to be sketching graphs like we've done in the past, but we're going to have arrows to indicate the direction of motion. So let's have a little look at this first example. We're going to sketch the graph of this. We've got r as a function of t equals 6 cos ti plus 3 sin tj. So this is our x as a function of t, and this is our y as a function of t. So x of t was 6 cos t. And as a reminder, let's write this before I get into that, sin t. This is what you used to do to be able to convert this into Cartesian form. You would use those trigonometric identities that I previously spoke about, and you're not just, going in the dark with this. You know that for something like this, when you have cos t and sine of t, and we've got different coefficients, we know that we're probably looking at an ellipse here. See, we've got cos t, sine t, or it could be sine t and cos t for the i's and j's, but we know we're headed for an ellipse. So, with this, what we're going to eventually be using is this identity, sine squared t plus cos squared t equals 1. That's the trick or the technique we use to go from these parametric equations to the Cartesian form, because we're trying to eliminate that t. So, let's write these. We know that, let's just write this as x, be 6 cos t. So cos t, not cost, will be x on 6. And we know sine t, sorry, I don't know why I wrote the t there, but not in another place. Sine t be y on 3. So when we go back to sine squared t plus cos squared t equals 1, sine t was y over 3, we'll square that. Cos t was x over 6, which we'll also square. Don't forget to put it in brackets because you've got to square both the numerator and the denominator. So we've got y squared on 9 plus x squared on 36 equals 1. Or you could have written that as 3 squared and 6 squared on the bottom there. Now, this is an ellipse. That's what we were suspecting it was going to be. So we need to draw an ellipse. This 9 tells us, because we don't have like y minus, I don't know, some constant there over 9, we know, because we also don't have a constant squared in brackets next to that x, that this ellipse is centered at the origin. We also know that the y values go between -3 and 3 because of that 9 underneath, and the x values are going between -6 and 6. Graphing this, we need this to go between -6 and 6, and we need this to go between 3 and 3. The big thing about drawing these ellipses is you need to remember the gradient at these points needs to be 0. I've overemphasized it. And the gradient at this point and this point needs to be undefined. They actually check for that on the exam. And you need to do your best to make it somewhat symmetrical. Oh gosh, that was not a good start. Okay, oh, I'm really happy with that. Not so happy with that. Look, not the best in the world, but not too bad. Let's label some points. Okay, so we've got the basic shape. I really want to use the ink to shape. No, I'm not going to do it. So we've got the basic shape. Again, a little bit dodgy here. I notice that this distance is significantly larger than this distance, so try and make it a bit more even than I have. Now, we need to include the direction of motion. So to do that, you can just do that by a bit of inspection here. If you substitute in t equals 0, we're going to have 6 cos of 0, so this is going to be 6, 6i, because we've got that I, and then 3 sine of 0, so it's going to be 0. So that means we start here. That's when t equals 0. And then we're going to be moving in this direction. You could check, you could substitute in another point, perhaps pi over 2 for t, and then pi, and 3 pi over 2. But you'll notice that you get a lovely continuous traveling in this direction. I've probably drawn too many arrows, but I made it abundantly clear which direction we're going in. Okay, using the CAS, nice and easy, you can go to, in the Casio, the graph and table menu. Notice for either of these though, it doesn't give the direction of motion, so you're going to have to manually put that in yourselves. Okay, let's have a look at another one. Bit different here. We want to sketch the path of a particle when the position at time t is given by, and this is our first one. We've got r is going to be 2ti plus t squared j, where t is greater than or equal to 0. So this is our x, this is our y, so we know x is 2t, y was t squared. And if we want to put that into Cartesian form to help us visualize, let's eliminate that t. So the x equals 2t tells us that t equals x over 2. So substituting that into here, we can have x over 2 squared. So x to the power of 2 over 4. Now take care, our Cartesian equation doesn't tell us about the direction of motion, but it doesn't also reflect naturally that restriction upon t. So they've told us that t is greater than or equal to 0. And if we look at that, substitute t equals 0 into here, we're going to have the 0 vector. So we're starting at the origin, and then we've got a lovely quadratic that's going to be headed off like that. Because here, remember, we were told t was greater than or equal to 0. Any of these parts of the parabola, which we're not drawing, that would be for t is less than 0. So we could have a very similar equation here, but instead of 2ti plus t squared j, we could have had this. If you use the technique to eliminate the t to find the Cartesian equation, you actually get the same Cartesian equation, so the same Cartesian path, but the rate at which the particle moves would be different. You could also get same Cartesian equation by chucking a negative out the front of one of them. But in this case, x would be less than or equal to 0, so the motion along the curve and the direction would be a little bit different. So just take care, the Cartesian equation obscures some of the details, so you need to still refer to that position vector and any restrictions upon t to be able to know what this particle is doing. Cartesian's still useful because we are familiar with this and we're quite good at graphing it, but we need to put a little extra thought into it. Okay, we have a nice one here. We've got an object moves along a path where the position vector is given by this. And we want to describe the motion of the object. So have a little think. You might want to substitute in some values of t, or have a little look more closely at what the x, y, and z values are doing. Pause if you need to. Now, I notice, regardless of the value of t, we've always got this vector 2k. So what's that effectively doing? So we've got our x, y, z. It's effectively moving our vector up by 2 units. So we're always going to have it acting on this plane. Oh, how am I going to draw that? That plane is parallel to the xy plane, and we're going to be restricting the motion of our particle here. Haven't looked at what that particle's doing, but it's always going to be 2 units up in the z direction. So let's look at what it's going to be doing on that plane. We've got cos ti plus sine tj. It's going to be going in a circle on that plane. So let's describe the motion of that object. Now, as that value of t changes, we're going to have that cos and that sine. There's no coefficients out the front. So this is just going to be nice circular motion, and in fact it's going to be constant speed in a circle. Now, just a note, this does not equal constant velocity. Constant velocity would mean that it's not changing direction, but by definition, something in a circle is always changing direction. Now, another thing, it's not just in a circle. We said that it was 2 units up on the z-axis. Now, we can actually 3D graph that on the CAS to check. So on the Casio, you're going to go to the 3D graph area, and you need to put in the parametric equations for x, y, and z as functions of t. So I'm going to show you that on the calculator. Give me one sec. Okay, for this we need to go into the 3D graph area, and you'll notice by default it just says Z equals. So what we do is we click on this button here, it'll toggle it between its different views. So we want those three parametric equations there. So let's type those in. Okay, so in that trig menu, just use the T for the parameter here. And now we want to graph it. So we'll click on that, and we're going to click on this button here. Now you'll notice at the moment, I'm moving that around, it's really difficult to sort of get an idea of what that's doing. So if you tap on this button here, and you'll see it toggles through some different options. I quite like this one. Oops, sorry, it's gone too far. I quite like this one because I can see where it is on that Z axis. But if you're having trouble visualizing the three-dimensionality of it, if you tap on it again to have a look with that cube, it can help you visualize. I quite like it just with the axes, and I like my axes labeled. And as I said, use this to toggle the axes. Now, I haven't confirmed this on the TI, but have a little check. I've put what someone suggested as the options that you need to go through to get this. Have a go and see if that works for you. Okay, let's look at a modified exam question. We've got the position vector of a particle at any time t is given by this. This is just 2 dimensions. And we're told t is in between 0 and pi on 2 inclusive. We want to find the Cartesian equation for the path followed by the particle and sketch the path followed by the particle on the axes below. Okay, so let's extract those parametric equations. Let's just write x instead of x of t because we're going to be rearranging. So x will be 2 cos of 2t. And we've got y is 3 sine 2t. Cos 2t is going to be x on 2. And we've got sine 2t. I know I went to having brackets. Sorry, having brackets then not having brackets, but just deal with it. Now, you might be a bit concerned at first that we have cos 2t and sine 2t, but that's okay because sine squared of 2t plus cos squared of 2t is still equal to 1. That's going to be nice because we can eliminate that t by substituting. We had that sine was y over 3, and we've got to square it. That cos was x over 2, which we're going to square. Oops, y squared over 9 plus 4 equals 1. Now, pause. We can see, hopefully you can see, that this is an ellipse. We can see that the ellipse is going to be between -2 and 2 in the x direction, -3 and 3 in the y direction. However, we have this restriction on t. T was in between 0 and pi on 2 inclusive. So we need to know where is the start point going to be and where is the end point going to be. So let's just substitute in t equals 0 and let's put it into our vector equation. R when t is 0 is going to be 2 cos of 0 plus 3 sine of 2 times 0 is still 0. So that's going to be 2, I, j. So it's going to be 2i plus 0. So 2i means we're going to be starting here. And let's go to pencil actually. So this is our start point when t equals 0. Then the end point is when t was pi on 2. So we're going to have 2 cos of 2 times pi on 2 I plus 3 sine 2 times pi on 2 j. So 2 times cos of pi is going to be -2i, and then 3 times sine of pi is going to be 3 times 0. So -2i means that we are going to be ending here. That's when t is pi on 2. So again, don't just rely on those Cartesian equations. We need to know what that path is, where it starts and where it ends. So I like using those endpoints. So you might draw something that looks like this for your Cartesian equation, and unfortunately, you wouldn't get full marks. Number 1, because I missed the point, but number 2, you need to make sure that the gradient is undefined there. So let's do that. Curving in. undefined. Oh, that one was a bit dodge. Come on. That looks a little too egg-like. Let's have another go. I need to make sure that it doesn't look like I'm trying to draw a circle. Look, I'm not happy with it, but I'm not unhappy with it. Now, assessor's report. Most students were unable to apply the domain restrictions correctly, and there was a problem with the similar question on last year's paper. So this was a 2007, 2006, they also struggled. Full ellipses were drawn or quarter ellipses, and when it says ellipses were not very elliptical, it's talking about those, I was going to say corners of the ellipse. I think I always say that, but you know what I'm talking about, the up, down, left, right extreme points. You need those undefined and zero gradients for it to be elliptical. I love the shade that's thrown in this. There were some very strange shapes provided. That makes me laugh. Okay, thanks. You've finished this portion. I will put the next one into a second video.